Hello, my dear dreamers, and welcome back to Happy Sleep. Whether you're joining me from a bustling city where the lights are just beginning to twinkle, a quiet countryside where the night is deep and still, or somewhere where the sun is high in the sky, I'm so incredibly glad you're here to unwind with me. Tonight, we are going on a journey unlike any other. We're going to leave all our daily worries right here on Earth and travel across the cosmos, back to the very beginning of everything, to witness the most powerful and catastrophic events our universe has ever known. We'll be exploring the 10 most apocalyptic moments ever recorded in cosmic history, from the violence that created the universe to the silent, future death of our own sun. So, find your most comfortable position, close your eyes, and let your mind drift among the stars. If this journey through the cosmos helps you relax or sparks your imagination, please do support our little channel by hitting that subscribe button and giving this video a like. It truly helps us grow and create more peaceful content for you. And I'd love to know, where in the world are you listening from tonight, and what time is it for you? Let's create a little constellation of our own in the comments below. Now let's begin our journey through time and space, to a silence deeper than any we can possibly imagine. Imagine for a moment the deepest silence you can possibly conceive. Not the quiet of a library or a remote forest at night, but a true, absolute, and profound silence. A silence so complete it has weight, a presence. This is the silence of the void between galaxies, a cosmic backdrop against which the most incredible, violent, and majestic events have played out for billions of years. Our universe, for all its serene, star-dusted beauty, has a resume stained with cataclysm. It is a born storyteller, and its favorite genre is epic disaster. Today, we are going to listen to its greatest hits, the top 10 most catastrophic events ever recorded in the history of everything. So, settle in, get comfortable, and prepare for a journey across eons and across light years, a tour of the absolute worst days in cosmic history. Our story begins not with a whimper, but with a bang. And not just any bang. The bang. The one that started it all. This is, without a doubt, the #1 catastrophic event, because it was the event that created the very concept of an event. The Big Bang, around 13.8 billion years ago, was the ultimate release of energy, the granddaddy of all explosions. Now let's really unpack that, because it's an idea that's so big, our brains almost want to push it away. It's like trying to imagine the color of a sound, or the taste of starlight. It feels unnatural. But let's try. We're going to slow down that first moment and really wander through it, because understanding this first greatest catastrophe is the key to understanding everything that follows. So, this singularity. Let's not just gloss over that word. It's a word scientists use when the math breaks down, when our understanding of physics just throws its hands up in the air and says, I quit. Imagine taking the entire universe, every galaxy, every star, every planet, every mountain, every person, every atom and everything that ever was or will be, and crushing it down. Not into something the size of a planet, or a city, or even a pinhead. We're talking about crushing it down to a point so infinitesimally small it has no size at all. Zero volume. It's a concept, not a place you could visit. All that reality, all that potential, was contained in a speck of unimaginable density and heat. The temperature was, well, the word temperature almost doesn't apply, because it was beyond anything the laws of physics, as we know them, can describe. It was a state of pure, undifferentiated energy. There was no space around it, because there was no around. There was no time before it, because time itself was born in that instant. This is the hardest part to grasp. We are used to things happening in time and in space. This was the moment time and space began, and then the decision was made. We don't know what flicked the first domino. Was it a random quantum fluctuation, a law of physics from a higher dimension, the work of a creator? Science, honestly, doesn't have a definitive answer yet, and that's okay. The wonder is in the mystery. What we do know is that this singularity decided to become a universe, And it didn't just expand, it inflated. This is another one of those words that doesn't quite do the event justice. We're not talking about a balloon filling slowly with air. We're talking about a transformation so rapid, so violent, and so utterly immense that it defies all human experience. In the first sliver of a second, to be precise, from 10 to power minus 36 to 10 to power minus 32 seconds after the initial moment, the universe underwent a growth spurt that makes everything since look utterly sedentary. It doubled in size and then doubled again and again and again in a cascade of doubling so fast that in that tiny, almost non-existent fragment of time, the universe expanded by a factor of at least 10^26. That's a 1 followed by 26 zeros. Let's try to picture that. Imagine a single grain of sand, smaller than you can see. Now, in the time it takes you to blink, that grain of sand expands to become trillions of times larger than the entire observable universe we see today. That's inflation. It was faster than the speed of light. Now, you might have heard that nothing can travel faster than light, and that's true for things within space. But space itself, the stage upon which the actors perform, the stage can stretch, and it can stretch at any speed it likes. There's no cosmic speed limit for the expansion of the fabric of reality itself. This inflationary period was the ultimate act of smoothing things out. It took whatever tiny quantum wrinkles and lumps might have existed in the primordial singularity and stretched them out to such a vast scale that the universe, on the largest scales, became incredibly uniform and flat. Think of a crinkled piece of paper. If you could stretch that paper to the size of a galaxy, any single crinkle would be so vast and stretched out that it would appear perfectly flat to a tiny ant on its surface. That's what inflation did for our cosmos. It set the stage for the large-scale structure we see today. And with this immense stretching came an unbelievable release of energy. This energy wasn't just heat and light, it was the raw material for everything. As the universe expanded and cooled, this pure, primordial energy began to condense, to freeze into the most basic particles, following the blueprint of the fundamental forces that were also emerging from this soup. What are these forces? Well, imagine they are the rules of engagement for the universe. First, there's gravity, the shy, long-distance attraction. It's the weakest force, but it never turns off and it works over infinite distances, patiently pulling things together. Then there's electromagnetism. This is the force that makes chemistry happen. It holds atoms together, it creates light, it's the reason you don't fall through the floor. It's the force of structure and connection. Then you have the strong nuclear force. This is the mighty glue that holds the nuclei of atoms together. It's incredibly powerful, but its reach is incredibly short, confined to the tiny space inside an atom's core. Without it, every atom in the universe would fly apart in a cloud of positively charged protons repelling each other. And finally, the weak nuclear force, which is responsible for radioactive decay and helps power the sun. In that first searing hot moment, these forces were believed to be unified, one single superforce. But as the universe cooled during inflation and just after, they underwent a series of phase transitions, like water freezing into ice, and they separated out into the 4 distinct forces we know and love today. Now, with the forces in place and the universe cooling, the energy soup could start to make some real particles. But not atoms. Not yet. We're talking about a zoo of exotic fundamental bits. In the first millionth of a second, the universe was a thick, opaque broth of quarks, gluons, electrons, and neutrinos, all zipping around at near light speed in an unbearable heat of trillions of degrees. This is called the quark epoch. Quarks are the building blocks of protons and neutrons, but it was still too hot for them to stick together. They were like people in an incredibly crowded, energetic mosh pit, constantly slamming into each other but unable to form any lasting partnerships. As the universe continued to expand and cool, it crossed a critical threshold. It was like the mosh pit calming down just enough for people to find their friends and link arms. This was the Hadron epoch. Quarks finally managed to bind together in groups of 3, held by the strong nuclear force, to form the first protons and neutrons. But it was still a violent world. For every particle of matter created, It's thought a particle of antimatter was also created. Matter and antimatter are like perfect opposite twins. When they meet, they annihilate each other in a flash of pure energy. In a perfectly symmetrical universe, all the matter and all the antimatter should have completely wiped each other out, leaving behind a universe of nothing but light. But we're here, made of matter, so something went wonderfully, catastrophically wrong. There was a tiny, tiny asymmetry. For every billion pairs of matter and antimatter that annihilated, one single particle of matter was left over. That 1 in a billion leftover is everything. Every star, every galaxy, every person you've ever met is made from that 1 in a billion relic. The cosmic debris from the great matter-antimatter annihilation. The rest became the vast sea of photons that would go on to become the cosmic microwave background. So, in a very real way, we are the ashes of that first, greatest conflict. The universe is now just a few minutes old. It has cooled to a mere 1 billion degrees, which is practically chilly by the standards of this story. This is when the next great act of construction occurs: Big Bang nucleosynthesis. For a brief window of about 17 minutes, the entire universe becomes a nuclear fusion reactor. The protons and neutrons, now stable, began to collide and stick together. A single proton is a hydrogen nucleus. A proton and a neutron stuck together make a deuterium nucleus, a heavy form of hydrogen. Then, these deuterium nuclei could collide with more protons and neutrons to form helium. It was a frantic, universal cooking session. In just those few minutes, the basic chemical composition of the universe was set. About 75% hydrogen and 25% helium, with trace amounts of lithium. And that was it. Every other element in the periodic table, the carbon, oxygen, iron, gold, would have to wait for the furnaces of stars billions of years later. This first, simple recipe is still what most of the universe is made of today. For the next 380,000 years, not much dramatic happens, at least in terms of structure. The universe is still a hot, dense fog of plasma. Electrons are zipping around freely and light is trapped, bouncing from one electron to another, unable to travel any distance. It's like being in the middle of the densest, thickest fog you can imagine, where you can't see your hand in front of your face, only this fog is made of pure energy and particles. But the universe keeps expanding, and expanding means cooling. Finally, it cools enough for the electrons to be captured by the atomic nuclei, forming the first stable, neutral atoms. This is recombination. The second most catastrophic and the important event was the flashbulb moment. The moment the last electron is snatched up, the universe changes in an instant. The fog clears. The photons, which had been trapped for 380,000 years, are suddenly set free. They fly through the now transparent universe in every direction. This is the flashbulb moment, the release of the cosmic microwave background radiation. That light is still traveling today. When we point our radio telescopes at the sky, this is the faint, ancient whisper we detect. It's the oldest thing we can ever see. It's a baby picture of the universe, taken when it was a mere 380,000 years old. The patterns in that light, the tiny variations in temperature that are just millionths of a degree, are the seeds of all future structure. Those slightly denser, slightly cooler spots are where gravity would eventually get to work, pulling in more matter, forming the first stars and galaxies. So, when you look at a static-filled, old-fashioned television set, about 1% of that snow is the literal afterglow of the Big Bang, the cooled-down remnants of that first catastrophic flash of light. It was a catastrophic change of state, a universal clearing of the air that allowed the cosmic dark ages to begin, setting the stage for the next great act, the birth of the first stars. Number 3 on our list is the birth of the first generation of the stars, and what a birth it was. After the brilliant flash of recombination, when the universe became transparent and let that first light, the cosmic microwave background, travel freely, a profound silence fell. This wasn't a peaceful silence, but an empty one. For millions of years, the cosmos was a vast, featureless expanse of cooling gas. There were no stars, no galaxies, no sources of light or heat beyond the fading afterglow of the Big Bang itself. This was the cosmic dark ages, a time when the universe was, quite literally, in the dark. But gravity is the most patient and persistent force in the cosmos. It never sleeps. Tiny, random quantum fluctuations from the inflationary epoch, those tiny wrinkles we mentioned earlier, were now the seeds of destiny. Where the gas was just a tiny bit denser, gravity had a slightly stronger grip. Over eons, these slight overdensities began to pull in more and more of the surrounding hydrogen and helium gas. Imagine a cosmic tapestry being woven, but incredibly slowly, with filaments of dark matter, that mysterious, invisible stuff that makes up most of the universe's mass, acting as the loom. The ordinary gas, the hydrogen and helium, was drawn into this dark matter scaffold, flowing along these invisible filaments and pooling at the nodes where they intersected. These were the first proto-galaxies, the cradles where the first stars would be born. Now, the formation of a star today is a well-understood, if still magnificent, process. It happens in cold, dense clouds of gas and dust that are rich in heavy elements. These metals, as astronomers call any element heavier than helium, are incredibly efficient at cooling the gas. They act like a radiator in a car engine, allowing the heat to escape. When the gas can cool efficiently, it can collapse into much smaller, denser clumps. This is why we have stars like our Sun, and even smaller red dwarfs. But the first stars, population the 3 stars, had none of these advantages. Their nursery was a cloud of pure hydrogen and helium. There was no dust to shield parts of the cloud, no carbon or oxygen to help it cool down. The only coolant available was a trace amount of molecular hydrogen, formed when 2 hydrogen atoms briefly joined together. This molecular hydrogen is a pathetically weak coolant compared to modern metals. It's like trying to cool a raging inferno with a single ice cube. This inefficiency had a monumental consequence. Because the gas couldn't cool down very much, it couldn't fragment into small pieces. The minimum mass needed for a cloud to collapse under its own gravity, what scientists call the Jeans mass, was enormous. So when these first clouds finally did collapse, they didn't break up into hundreds of little stars. Instead, they collapsed as a single, gigantic entity, funneling the mass of hundreds of suns into a handful of stellar embryos, or in many theoretical models, just one truly monstrous star. This is the key to understanding why population 3 stars were the behemoths we describe them as. The physics of the pristine universe demanded it. The conditions were simply not right for making modest, long-lived stars like our Sun. The universe, in its youth, only knew how to build on a grand, catastrophic scale. So, within these spinning, collapsing clouds, a protostar began to form. A protostar is the infant stage of a star before nuclear fusion ignites in its core. It shines not from fusion, but from the sheer heat of contraction. The gravitational energy of all that gas falling inward is converted into intense heat. For a modern star like our Sun, this protostellar phase lasts about 50 million years. For a population 3 star, it was a much more frantic, violent process. As more and more gas rained down onto the growing core, the pressure and temperature at the center began to skyrocket. The core became a roiling, chaotic place, and for a brief period, it's even thought that a special kind of nuclear fusion occurred, involving the heavy isotope of hydrogen known as deuterium. This deuterium fusion helped to temporarily stabilize the young star, inflating it and buying a little time, but it was a mere prelude to the main event. Then, the moment of ignition arrived. Deep within the core, the temperature finally reached a staggering 10 million degrees Kelvin. At this threshold, the protons, the nuclei of hydrogen atoms, were moving so fast that they could overcome their natural electromagnetic repulsion and get close enough for the strong nuclear force to take over, slamming them together to form helium. Hydrogen fusion had begun. The nuclear furnace was lit. And what a furnace it was! In a star, there is a constant battle between 2 immense forces: the outward pressure from the radiation generated by fusion and the inward crush of gravity. In a star like our Sun, this is a stable, balanced fight that has lasted for billions of years and will continue for billions more. But in a population 3 star weighing in at 100 200, or even 300 solar masses, this balance was a frantic, high-stakes arms race. The gravitational pressure at the core of such a monster was almost incomprehensible. To hold up against this crushing weight, the star had to fuse hydrogen at a ferocious, runaway rate. It was like trying to hold up a collapsing skyscraper by detonating a continuous series of nuclear bombs in the basement. The star was living on borrowed time from its very first breath. This leads us to their incredible characteristics. If these stars were indeed so massive, they were also unbelievably hot and bright. A star 100 times the mass of our Sun wouldn't be 100 times brighter, it would be millions of times brighter. Our Sun has a surface temperature of about 5,800 Kelvin. A massive population 3 star could have a surface temperature of 100,000 Kelvin or more. At that temperature, a star doesn't emit the friendly, warm, white light of our Sun. It is a searing, blistering, blue-white inferno, and almost all of its energy is pumped out not as visible light, but as high-energy, ionizing ultraviolet radiation. This radiation was the key that unlocked the next chapter of the universe. For the first 400 million years or so, the hydrogen gas between galaxies was neutral. Its electrons were snugly orbiting their protons. But the intense UV light from these first stars began to rip the electrons away from the protons in a process called ionization. This ended the cosmic dark ages and began the epoch of reionization, a fundamental phase change for the entire universe, lifting the fog and making the intergalactic medium transparent once again, a state it has maintained ever since. These stars were not just objects in the universe. They were actively changing the universe, sculpting its very structure with their brilliant, deadly light. But such a profligate lifestyle cannot last. A star like our Sun has a life expectancy of about 10 billion years. It is a frugal, efficient burner of its hydrogen fuel. A 100 solar mass population 3 star, by contrast, would live for only 2 to 3 million years. That's not even a blink of a geological eye. It's less than the time that has passed since the earliest ancestors of humanity first walked the earth. They lived fast, and they were destined to die young, and their deaths were as consequential as their births. The fate of a star is dictated by its mass. When it runs out of fuel in its core, the balance of power tips and gravity wins the final battle. For these first stellar giants, their deaths were spectacular cosmic fireworks shows that we can barely imagine, and they came in a few different varieties, all of them catastrophic. For the stars at the lower end of the population 3 mass range, say between 10 and 140 solar masses, their deaths would have been in the form of core collapse supernovae, similar to what we see today, but on a grander scale. When their cores ran out of fuel, the radiation pressure dropped and the core collapsed in a fraction of a second into an incredibly dense neutron star or a black hole. The outer layers of the star, no longer supported, would come crashing down and then rebound off the hard surface of the new neutron star in a titanic shockwave, blasting the star apart and scattering its newly forged guts across space. But for the real behemoths, those between about 140 and 260 solar masses, something even more extreme occurred: the pair instability supernova. This is the catastrophe you mentioned, and it's worth savoring every detail. In the final stages of its life, the core of such a star becomes unimaginably hot. The radiation bouncing around inside is so energetic that it spontaneously transforms into matter, creating pairs of electrons and their antimatter counterparts, positrons. Now, this might not sound like a big deal, but in the delicate balance of a star's core, it's a disaster. Radiation pressure is a key part of what holds the star up. When radiation turns into these particle pairs, that pressure suddenly drops. It's like someone pulled a crucial support beam out from a building. With the pressure gone, gravity surges inward and compresses the core even further, which in turn makes it even hotter. This triggers a runaway frenzy of nuclear fusion. In an instant, the entire core fuses into heavier elements like iron, nickel, and radioactive nickel. The energy release is so instantaneous and so violent that it doesn't just blow the star's outer layers away. It completely and utterly obliterates the entire star. There is no remnant, no neutron star, no black hole. The entire star is turned inside out and scattered across space in an explosion so bright it would outshine an entire galaxy of modern stars. The sheer power of this event is the key to our existence. In these blasts, the first significant quantities of elements heavier than helium were forged and dispersed. Carbon, oxygen, silicon, iron, gold, all the raw materials for planets, oceans, and life itself were minted in these first catastrophic stellar explosions and seeded into the primordial gas clouds. And for the very largest of the population 3 stars, those above 260 solar masses, their fate was perhaps the most mysterious of all. Their gravity was so overwhelming that even a pair instability supernova couldn't occur. When their cores ran out of fuel, there was no last-minute reprieve, no explosive rebellion. Gravity won an absolute and total victory. The entire star would have collapsed directly into a black hole, swallowing all of its newly created heavy elements without a trace. It would have been a quiet, dark end for a brilliant life, but these black holes may have gone on to become the seeds for the supermassive black holes that lurk at the centers of galaxies today, including our own Milky Way. So this is the legacy of the population 3 stars. They were the pioneers, the universe's first, clumsy, and magnificent attempt at making something more complex than simple hydrogen and helium. They lit up the darkness, they reionized the cosmos, they forged the elements of life in their cores and in their spectacular deaths, and they likely planted the seeds for the giant black holes that would one day anchor galaxies. They are the reason we are here. Every atom of oxygen in the air we breathe, every piece of calcium in our bones, every speck of iron in our blood was at one point inside one of these long-vanished giants. We are, all of us, the stardust from the universe's first and greatest catastrophes, and the hunt for them continues. We have not yet directly observed a single definitive population 3 star. They are all gone, and the ones that might have been small enough to survive are too faint and too far away, their light stretched into the infrared by the expansion of the universe. But NASA's James Webb Space Telescope, with its powerful infrared eyes, is designed to peer back to this very epoch. It may not see an individual star, but it might see the telltale glow of galaxies that contain them, or even the brilliant flash of a pair instability supernova going off in the early universe, the final fading signature of a true cosmic titan. The story of the first stars is not yet fully written. We are still listening for their echoes, still trying to catch a glimpse of the light that ended the universe's long dark night. As the first stars lived and died, they began to congregate, drawn together by gravity into the first proto-galaxies. This leads us to the number 4 catastrophe, one that involves the very heart of these nascent galaxies, the awakening of supermassive black holes. So, we have our first galaxies, cobbled together from the ashes of those magnificent population 3 stars. But within the chaotic core of these nascent islands of stars and gas, a deeper drama was unfolding. Lurking in the center was a seed of unimaginable density, a relic from the universe's wild youth. Now, what were these seeds? That, to this day, remains one of the great puzzles of cosmology. Perhaps they were the leftover black holes from the very first pair instability supernovae, weighing in at a few hundred solar masses. Or maybe, in the incredibly dense environments of those first proto-galaxies, entire clusters of stars collapsed directly into a single, much larger black hole in a runaway chain reaction of collisions and mergers. There's even a fascinating theory that they could have formed from the direct rapid collapse of enormous clouds of primordial gas, skipping the star-forming stage entirely, and just, voila, a black hole of tens of thousands of solar masses born in an instant. Whatever their origin, these seeds were the sleeping monarchs of their infant galaxies waiting for their coronation. And the coronation ceremony was a feast. In the crowded, gas-rich core of a young galaxy, vast rivers of hydrogen and helium, the legacy of the Big Bang and enriched by the first stellar generations, began to flow toward the central gravitational pit. Now, here's a crucial point. We often imagine matter falling straight into a black hole, but it rarely does. Because the gas cloud has some inherent spin, a property conserved from the tiny motions of the early universe, it can't fall directly in. Instead, it's like water circling a drain. The infalling gas forms a vast, flattened, spinning structure around the black hole called an accretion disk. This is where the magic and the catastrophe truly begins. The material in this disk is packed incredibly tightly, and as it spirals inward at speeds approaching a significant fraction of the speed of light, the particles of gas rub against each other with unimaginable violence. The friction from this is so intense that it heats the gas to temperatures of millions of degrees. At these temperatures, the disk doesn't just glow with visible light. It becomes a furnace that blazes with high-energy X-rays and gamma rays, the most energetic forms of light in the universe. It is this process of accretion, the slow, spiraling descent of matter into the abyss, that powers the most luminous objects we have ever discovered. This is the birth of a quasar, a term short for quasi-stellar radio source. When these objects were first identified in the 1960s, they appeared as pinpoint stars of light on photographic plates, but their spectra told a bizarre and revolutionary story. The light from these stars was dramatically redshifted, indicating they were not only incredibly far away, billions of light years distant, but also that they were moving away from us at tremendous speeds due to the expansion of the universe. The staggering implication was that to appear so bright from such an immense distance, a single quasar had to be outputting the energy of hundreds of normal galaxies, all from a region not much larger than our solar system. It was an energy output that defied comprehension, and for a while, scientists scrambled for an explanation. The only engine powerful enough, the only conceivable power source that could fit in such a small space, was a supermassive black hole in the midst of a glorious, universe-shaking feeding frenzy. Now, the physics of this environment is truly mind-bending, warping the very rules of reality as we know them. The accretion disk is only part of the story. Some of the infalling material, instead of crossing the event horizon, gets caught up and focused by the black hole's immensely powerful magnetic fields. These fields act like a cosmic particle accelerator, funneling this superheated gas into two narrow, oppositely directed jets that erupt from the black hole's poles, shooting outward at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, far beyond the boundaries of their host galaxy, punching into the intergalactic void. They are like the blowtorches of gods, and they are visible across the electromagnetic spectrum, particularly in radio waves, which is how our telescopes often first detect them. The sheer power involved is almost impossible to overstate. Imagine taking the entire mass of our sun, converting it into pure energy, and releasing it every single year. That is the kind of apocalyptic budget a feeding supermassive black hole operates on. It is a bottomless cosmic drain, yes, but one that, in the act of consumption, screams its existence across the cosmos with a flash of light that can be seen clear across the universe and back to the dawn of time. This violent awakening was not just a spectacle, it was a fundamental force of cosmic regulation. This is a concept astronomers call feedback, and it's the crucial role these active black holes play in the life story of galaxies. In their ferocious youth, these quasars and their powerful jets acted as a cosmic thermostat for star formation. How? Well, a galaxy is full of the raw gas needed to form new stars. Left to its own devices, a gas-rich galaxy might form stars in an unchecked frenzy. But when the central black hole switches on, the incredible energy it releases, in the form of radiation and those powerful jets, heats up the surrounding gas, or simply blows it clean out of the galaxy. Think of it as a cosmic hairdryer, as one researcher put it, set to maximum power, blasting away the very fuel for future stars. By doing this, the black hole effectively limits its own food supply while also putting a cap on the number of new stars the galaxy can create. In some cases, the shock waves from these jets might also compress distant gas clouds, actually triggering new, localized bursts of star formation. So they are both destroyers and creators, architects shaping their galactic homes from the inside out. This feedback process is why we don't see many gigantic, bloated galaxies today. The supermassive black holes at their centers, in their wild quasar youth, prevented them from growing any larger. The quest to understand these cosmic leviathans is more exciting than ever, as our technology allows us to witness their behavior in real time. Just recently, in August of 2025, astronomers announced a breathtaking discovery. They caught a supermassive black hole in the act of waking up in a galaxy cluster far, far away. Using the incredible resolution of the Very Long Baseline Array, VLBA, a network of radio telescopes that can see details equivalent to reading a newspaper in Los Angeles from New York, they observed a black hole that had only begun its active phase about 1,000 years ago, a mere blink in cosmic time. Its jets were just 100 light-years long, mere infants compared to the mature jets that span tens of thousands of light-years. This is like finding a picture of a giant in its crib, giving us an unprecedented before picture of black hole feedback, a chance to watch the story unfold from the very first page. Furthermore, new research is challenging our very understanding of how big these early giants were. For years, astronomers were puzzled by the existence of what appeared to be fully grown supermassive black holes in the very early universe. They simply shouldn't have had enough time to get that big. But in September 2025, using a powerful new instrument called Gravity Plus, scientists peered into the heart of an ancient quasar and found its black hole was actually 10 times smaller than previous estimates had suggested. It seems some of these early black holes were not the fully formed titans we thought, but were instead in the midst of such violent feeding frenzies that the intense radiation they produced was tricking our telescopes into thinking they were more massive than they truly were. This is a monumental finding, one that may solve a long-standing cosmic puzzle and force us to reevaluate our models of how the universe evolved. And let's not forget our own local supermassive black hole, Sagittarius A star, sitting quietly at the heart of the Milky Way. In 2022, the Event Horizon Telescope collaboration, the same team that brought us the first ever image of a black hole in the galaxy M87, released the first picture of our own galactic center's black hole. It was a monumental technical achievement, made even more difficult than the M87 image because Sagittarius A star is much smaller, meaning the gas whips around its event horizon in mere minutes, like trying to take a clear photograph of a puppy chasing its tail. The resulting image, that iconic fiery donut of light surrounding a dark shadow, confirmed beyond any doubt the existence of this colossal object, a 4.3 million solar mass giant sleeping in our own backyard. It's a relatively quiet beast today, only occasionally flaring up when it snacks on a passing cloud of gas or a stray asteroid. But its serene presence is a living relic, a reminder of a more violent past when our own galaxy's heart was a brilliant, active quasar, shaping the stars and worlds that would one day lead to us. So, you see, the awakening of the first supermassive black holes was more than just a catastrophe. It was the moment the universe developed a heartbeat. These brilliant, terrifying, active galactic nuclei were the regulatory engines that dictated the growth and form of galaxies. They scattered the heavy elements forged in stars across intergalactic space. They heated the cosmic voids, and they ultimately created a universe that was capable of fostering quiet, stable galaxies like our own Milky Way, where life could eventually arise on a pale blue dot and look up at the silent, dark center of our galaxy and wonder at the violent, glorious birth of the cosmic giants. While quasars were lighting up the early universe, another, quieter but equally catastrophic process was unfolding in the stellar nurseries of these young galaxies: the phenomenon of gamma-ray bursts. So, we have our quasars, these brilliant galaxy-scale beacons shining from the early universe. But while they were lighting up the cosmic stage, another, far more fleeting and violent kind of explosion was happening in the stellar nurseries within those galaxies. These are the gamma-ray bursts. To call them powerful is a laughable understatement. It's like calling a supernova a little spark. The numbers are so vast they become almost meaningless, but let's try to give them some perspective. Imagine taking our sun, a perfectly respectable star that has been steadily shining for 4.5 billion years, and will continue to do so for about another 5 billion. Now imagine it somehow, over its entire 10 billion year lifespan, releasing every single joule of energy it will ever produce. That's the sun's total lifetime energy budget. A single gamma-ray burst can release that much energy, or more, in the time it takes you to read this sentence. In just a few seconds, it can outshine an entire galaxy containing hundreds of billions of stars. It is, for a fleeting moment, the single brightest source of light in the entire observable universe, second only to the Big Bang itself in its raw, explosive power. The story of how we discovered these cosmic monsters is almost as incredible as the events themselves. It begins not with a quest for scientific knowledge, but with the tensions of the Cold War. Back in the 1960s, the United States launched a series of satellites called Vela. Their job was not to look at stars, but to watch for secret, illegal nuclear weapons tests that the Soviet Union might be conducting in the vacuum of space, in violation of an international treaty. These satellites were equipped with gamma-ray detectors, because nuclear bombs release a telltale flash of this high-energy light. On July 2, 1967, the Vela 4 and Vela 3 satellites detected something peculiar. It was a flash of gamma radiation, but it didn't match the signature of any known nuclear weapon. The team at Los Alamos National Laboratory, led by Ray Klebesattel, was puzzled. They filed the data away, but as more advanced Vela satellites were launched, they kept seeing these strange, inexplicable bursts. They weren't coming from Earth, and they weren't coming from the Sun. They were coming from deep space. After years of analysis, the findings were finally declassified and published in 1973 in a landmark paper titled Observations of Gamma-Ray Bursts of Cosmic Origin. The mystery had officially begun. For decades, astronomers were flummoxed. What could possibly create such unimaginably powerful yet incredibly brief flashes of light? The problem was that the initial gamma-ray flash was so short-lived that by the time astronomers could point their optical telescopes to the right patch of sky, there was nothing left to see. It was like trying to find the source of a camera flash in a dark, crowded room after the flash had already ended. Hundreds of theories were proposed, from comets crashing into neutron stars to alien starships going to warp speed. The breakthrough came in the 1990s with two key missions. First, the Compton Gamma Ray Observatory showed that these bursts were distributed evenly across the entire sky, proving they were not from our Milky Way galaxy, but from far, far beyond. Then, in 1997, the Italian-Dutch satellite BeppoSat performed a miracle. It detected a burst, and with incredible speed, its X-ray camera was pointed in the right direction. For the first time, scientists detected a fading X-ray signal, an afterglow. This afterglow was the key. It lasted much longer than the initial burst, and it shone in other wavelengths of light, like X-rays, visible light, and radio waves. Telescopes on Earth, including the mighty William Herschel telescope, quickly swiveled to look and identified a faint, fading pinpoint of visible light. Deep imaging later revealed that this pinpoint was located in an incredibly distant, faint galaxy. The mystery was solved. Gamma-ray bursts were extragalactic events, occurring billions of light-years away, which meant their energy was even more stupendous than anyone had dared to imagine. Now, as we collected more data, a clear pattern emerged. These bursts came in two distinct flavors, like two different types of cosmic bombs with completely different triggers. Astronomers, looking at data from instruments like the Burst and Transient Source Experiment, BEIT-SE, realized that when they plotted the duration of the bursts, they fell into two separate camps, the long-duration bursts and the short-duration bursts. The dividing line is set at about 2 seconds. This isn't just an arbitrary number, it points directly to two completely different catastrophic events that cause them. Let's start with the long-duration bursts, the ones that last from 2 seconds to several minutes, and sometimes even hours. These are the ones intimately tied to the death of the most massive stars in the universe. Picture a true stellar giant, a wolf among sheep, a star at least 20, 30, or even 40 times more massive than our Sun. It lives its life fast and hard, burning through its nuclear fuel in just a few million years. When it finally runs out of fuel, the outward pressure from fusion that has been holding the star up against its own immense gravity suddenly vanishes. The core, which can be several times the mass of our Sun, collapses in on itself. In a regular supernova, this collapse would rebound in a mighty shockwave. But in this case, the core is so heavy that there is no rebound. It just keeps collapsing in less than a second until it forms a black hole. But the story doesn't end there. This isn't a quiet, gentle collapse. The star has immense rotational energy, like a spinning figure skater pulling in her arms. As the core collapses, this spin is amplified to an insane degree. The newly formed black hole is surrounded by a swirling, superheated disk of leftover stellar material, a chaotic, cosmic whirlpool. This system acts like a natural engine. Powerful magnetic fields channel the incredible rotational energy into two narrow, oppositely directed jets of particles, which are accelerated to 99.9% the speed of light. These jets are like the blowtorches of a god, and they are so powerful and focused that they literally punch their way through the outer layers of the dying star, which are still in the process of collapsing inward. It is within these ultra-relativistic jets that the initial flash of gamma rays is created, as particles are accelerated and interact with magnetic fields and each other. What we see as a long gamma-ray burst is the birth cry of a new black hole, a beacon of light announcing that a stellar giant has died and a gravitational monster has been born. Weeks later, as the blast continues to expand, astronomers often see the brightening of a supernova, the final testament of the star's outer layers being blasted into space. Now let's turn to the short-duration bursts. These are the ones that last less than 2 seconds, sometimes for just a few milliseconds. They are briefer, but in many ways, their origin story is even more dramatic. The trigger here is not the death of a single star, but the final fatal dance of two long-dead stellar corpses, neutron stars. Imagine the remains of two massive stars that have already gone supernova. What's left behind are neutron stars, objects so incredibly dense that a single teaspoon of their material would weigh billions of tons on Earth. They are only about the size of a city, but they contain more mass than our sun. These two cosmic zombies can be locked in a mutual orbit, slowly but surely losing energy by emitting gravitational waves, ripples in the very fabric of spacetime as predicted by Einstein. Over billions of years, this loss of energy causes them to spiral closer and closer together. Their dance speeds up, becoming a frantic final embrace. When they finally collide, the impact is so violent that it creates a fireball of unbelievable density and heat. This collision also forges a new black hole almost instantly. Just as with the long bursts, this process can power incredibly powerful, focused jets, and the interaction within these jets produces that brilliant sub-2-second flash of gamma rays that we see as a short GRB. But the aftermath of this merger is where something truly magical happens. The collision blasts a cloud of neutron-rich material out into space. In this cloud, a frantic process called rapid neutron capture occurs, forming the heaviest elements in the universe. This creates a unique kind of explosion called a kilonova. The light from a kilonova is special because it is much brighter in near-infrared light than in visible light. This is because the newly created heavy elements like gold, platinum, and uranium in the debris cloud block the shorter wavelengths of visible light while allowing the longer wavelengths of infrared light to pass through. So, the next time you admire a gold ring or necklace, remember this. Most of the gold on Earth was likely forged in the cataclysmic kilonova explosion from the merger of two neutron stars, billions of years ago, in a galaxy far, far away. These short bursts are the universe's ultimate alchemists. The initial flash is just the beginning of the story. What follows is the afterglow, and it's just as important scientifically as the burst itself. As the high-speed jets from the burst plow into the thin gas of interstellar space, they create a massive shockwave. This shockwave acts like a natural particle accelerator, causing the material to glow brightly across the entire electromagnetic spectrum, from radio waves to X-rays. This afterglow can last for hours, days, or even years, fading all the while. It is this lingering glow that allows astronomers to pinpoint the burst's location, measure its distance, and study the environment where it occurred. It's like the smoke left after the gun has been fired, allowing detectives to find the shooter. Given their incredible power, it's natural to wonder what would happen if one of these cosmic sniper shots was fired in our direction. The truth is as terrifying as any science fiction. All the GRBs we have recorded have come from outside our Milky Way, from safe distances of billions of light years. But if a long-duration burst were to happen within our own galaxy, and if one of its deadly jets were pointed directly at Earth, the consequences would be apocalyptic. Scientists estimate that if one occurred within a few thousand light years of us, the effect would be an extinction-level event. The initial blast of gamma and X-rays would vaporize the daytime side of our planet. The bigger threat, even from a more distant burst, would be the after effects. The high-energy radiation would rip apart the molecules in our atmosphere, specifically targeting the ozone layer that protects us from the sun's harmful ultraviolet rays. With this protective shield destroyed, Earth would be bathed in lethal levels of UV radiation, devastating the food chain by killing phytoplankton in the oceans and causing widespread crop failure on land. It's been hypothesized by some researchers that a gamma-ray burst might have been responsible for the Ordovician mass extinction about 440 million years ago, which wiped out most life on Earth at the time. It's a sobering reminder that we live in a violent universe, and our peaceful existence here on Earth is a fragile exception in a cosmos that can, without warning, fire a shot across the bow. The study of GRBs is far from over. In fact, it's entering one of its most exciting phases. In 2017, a monumental event occurred that confirmed our theories about short GRBs and opened a new era of astronomy. For the first time, gravitational wave observatories LIGO and Virgo detected ripples in spacetime from the merger of two neutron stars. A mere 1.7 seconds later, NASA's Fermi satellite detected a short gamma-ray burst, GRB 170817A, coming from the same direction. This was the smoking gun that definitively linked short GRBs to neutron star mergers. For the first time, we had seen the same cosmic cataclysm in both light and gravitational waves, a technique now known as multi-messenger astronomy. Then in 2022, astronomers witnessed the BOAT, the brightest of all time. Officially named GRB 221009A, this burst was so powerful that it temporarily blinded most gamma-ray instruments in space. It was a long-duration burst, and it was also one of the closest ever seen, making its appearance in our sky a once-in-10,000-year event. Studying its brilliant light is helping scientists understand the finer details of how these jets operate and even map the hidden dust clouds within our own Milky Way. And the surprises keep coming. As recently as July 2025, an event designated GRB 250702b completely baffled astronomers. It defied all known logic by lasting for about a day, and even more strangely, it appeared to repeat, sending out multiple powerful bursts over several hours. This is something that should be impossible according to our current models, as GRBs are supposed to be one-off, catastrophic events that destroy their source. This strange event suggests that perhaps a star was being slowly torn apart by an intermediate mass black hole, or that we are seeing a completely new type of stellar death. It's a thrilling reminder that the universe always has new mysteries up its sleeve, and the story of these cosmic explosions is still being written, one brilliant, catastrophic flash at a time. Our own solar system has not been immune to the violent tendencies of the cosmos. Catastrophe number 6 takes us back to about 4.5 billion years ago, to the very chaotic beginnings of our planetary neighborhood. The early solar system was a shooting gallery, a vast disk of gas, dust, and planetesimals, the building blocks of planets, all orbiting the young sun. As these planetesimals collided and stuck together, they grew into planetary embryos and then into protoplanets. This period, known as the Late Heavy Bombardment, was a time of immense cosmic violence. The inner solar system was a battlefield, with dozens of Mars-sized bodies vying for position. The evidence of this catastrophe is written on the face of every airless world. The Moon, Mercury, and Mars are all covered in craters, the scars of this ancient bombardment. But the most dramatic event from this era, and the one that had the most profound consequence for us, was a specific, colossal impact here on Earth. A Mars-sized body, which scientists have named Theia, is thought to have slammed into the proto-Earth. The catastrophe is almost beyond comprehension. The impact was so violent that it is believed to have vaporized a significant portion of the early Earth, melting the entire planet and ejecting a colossal amount of material from both bodies into orbit around Earth. This ejected debris, a ring of molten rock, quickly coalesced under its own gravity to form our moon. This giant impact hypothesis explains so much about the Earth-Moon system, why the moon is slowly moving away from Earth, why it has a relatively small iron core, Theia's core merged with Earth's, and why moon rocks are so similar in composition to Earth's mantle. This catastrophic collision gave us our largest and most prominent natural satellite, which in turn stabilized Earth's axial tilt, giving us relatively stable seasons and creating the tides that may have been crucial for the emergence of life. From a world-shattering disaster came the very companion that has guided and inspired humanity for all of its existence. Sometimes the catastrophes are not from without, but from within. Our seventh catastrophic event is a homegrown one, but on a planetary scale. About 2.4 billion years ago, something happened on Earth that would forever change the atmosphere and the course of life. The Great Oxidation Event, a slow-motion apocalypse that unfolded over hundreds of millions of years, a drama where the villain was also the hero and the poison was also the elixir of life. To truly understand it, we have to travel back in time, to an Earth that would be almost unrecognizable to us. Picture this. It's about 2.4 billion years ago. The Earth is already ancient, over 2 billion years old. The continents are small, barren, and volcanic, likely tinged a strange shade of black or green due to different mineral compositions. There is no soil as we know it, just rock and dust. The sky is not blue, but a hazy, orangish, or even methane green pall, likely filled with a thick fog of volcanic gases and other compounds. The sun shines, but it's a fainter, younger star, putting out only about 80% of the energy it does today, and there is no oxygen, not a single breathable molecule in the entire atmosphere. The air is a toxic stew to us, composed largely of nitrogen, carbon dioxide, methane, and water vapor. If you were to step onto this primordial Earth with a time machine, your first and last breath would be a searing, lethal gasp. This is the Archean Eon, a world of profound strangeness, and yet a world teeming with life. But what life? Forget dinosaurs, forget fish, forget even worms. Life at this time was exclusively microbial, a hidden, subterranean, and oceanic world of single-celled organisms, and they were all, to a microbe, anaerobic. This is a crucial word. It means without air, but more specifically without oxygen. These ancient life forms did not breathe oxygen. In fact, they found it to be a deadly, destructive poison. Their metabolisms were based on much more primitive chemistry. Some, known as methanogens, consumed carbon dioxide and hydrogen, and as a waste product, they released methane, a powerful greenhouse gas that helped keep the planet warm under that faint young sun. Others performed a form of fermentation, breaking down simple chemicals released from volcanic vents or decaying matter. This was the established world order, a stable global ecosystem of anaerobes, living and dying in the oceans and sediments for over 1.5 billion years. It was a successful, stable, and deeply stagnant world. Then, a revolution began. It didn't start with a bang, but with a subtle biochemical innovation inside a tiny, unassuming cell. A new kind of bacteria evolved, the cyanobacteria. You might know them by their more common and slightly misleading name, blue-green algae. They were photosynthetic. Now, we learn about photosynthesis in school, but we rarely stop to consider how utterly revolutionary, how literally earth-shattering this process was. These tiny organisms had figured out how to capture the faint young sun's light, a constant streaming source of energy from the cosmos, and use it to power their lives. They use that solar energy to take water, simple, abundant H2O, and carbon dioxide from the atmosphere, and they smash the molecules apart, rearranging the atoms to form sugars for themselves. It was a brilliant, elegant bit of cellular machinery. But every process has a waste product. For us, when we burn sugar for energy, we exhale carbon dioxide. For the cyanobacteria, the waste product of their brilliant new solar-powered lifestyle was molecular oxygen, O2. They were, in effect, tiny living factories, pumping this new, highly reactive, and for every other organism on the planet, terrifyingly toxic gas into their surroundings. Imagine the scene from the perspective of the ancient anaerobic microbes. For eons, they had lived in a stable, oxygen-free world. Then, these upstart cyanobacteria appear in their microbial mats and slimy colonies, and they start spewing out a corrosive, destructive chemical. Oxygen is a highly reactive molecule. It's a voracious participant in chemical reactions, a process we commonly know as rusting or burning. To the anaerobes, whose delicate, unprotected cellular machinery was based on iron and sulfur, this free oxygen was like acid. It would have ripped through their cells, breaking apart their proteins, disrupting their metabolic pathways, and essentially causing them to rust from the inside out. The first cyanobacteria were, in effect, unleashing a slow, insidious, planetary-scale chemical weapon. So why didn't the atmosphere immediately fill with oxygen and wipe everything out? Because the young Earth had a sophisticated, planetary-scale immune system. The planet itself was a giant oxygen sink. This is where the story gets visually spectacular, and where we find some of the most important geological evidence for this entire event. The first and most important sink was dissolved iron in the oceans. The ancient seas were rich with iron, leached from the rocks by volcanic acids, and in the absence of oxygen, this iron was soluble, meaning it was dissolved in the water, giving the oceans a possible greenish or murky appearance. As the cyanobacteria began producing oxygen, this oxygen would immediately react with the dissolved iron. The iron would rust out of the water, forming particles of iron oxide that would slowly sink to the ocean floor. This process created vast sequential layers of rust on the seafloor. These are the famous banded iron formations, BIFs, that we mine today for most of the world's iron ore. Those beautiful red and silver layered rocks are the direct fossilized evidence of this global chemical battle. A battle between the oxygen produced by life and the iron dissolved in the oceans. Each band represents a pulse of oxygen production, followed by a period where the iron sink dominated. It was a slow, rhythmic war between biology and chemistry, fought over millions of years. Other oxygen sinks were also at work. Oxygen would react with volcanic gases like hydrogen sulfide. It would also react with the organic carbon from dead microbes that was buried in the sediments, or with minerals on the land surfaces. For perhaps 200 or 300 million years, this is how it went. The cyanobacteria, living mostly in protected microbial mats to shield themselves from their own poison, would produce a trickle of oxygen, and the planet, the oceans, the rocks, the air, would eagerly, hungrily mop it all up. The status quo was being challenged, but it was holding. The anaerobes could still survive, retreating to oxygen-free zones in the deep ocean or underground. The world remained largely anoxic. But then a tipping point was reached. This is the core of the catastrophe. We don't know exactly what pushed the system over the edge. Perhaps the cyanobacteria evolved to become more efficient, forming the first multicellular chains that allowed them to colonize new environments more effectively. Perhaps a shift in plate tectonics led to a reduction in volcanic activity, reducing the supply of fresh iron to the oceans or cutting back on other reducing gases. Perhaps the simple, relentless accumulation of dead organic carbon being buried on the seafloor faster than it could react with oxygen slowly used up one of the planet's major sinks. It was likely a combination of all these factors. But the day came when the cyanobacteria and their photosynthetic offspring were producing oxygen faster than all the natural sinks of the Earth could absorb it. And so, the oxygen began to leak. It built up in the oceans first, and then, for the first time in Earth's history, it began to accumulate in the atmosphere. This was the Great Oxidation Event. It wasn't a single day or year. It was a geological transition that may have taken 10 or 20 million years. But in Earth time, that's the blink of an eye. The evidence for this is locked in ancient rocks. We see the appearance of red beds, continental sandstones that are stained red by iron oxide, which can only form in an atmosphere with free oxygen. We also see the disappearance of detrital minerals like pyrite and uraninite, grains that are stable in anoxic conditions but instantly rust or dissolve when exposed to even tiny amounts of oxygen. For the established anaerobic life, this was the beginning of the end. It was the worst pollution event in the history of our planet. The rising tide of oxygen was a genocidal, toxic gas spreading through the oceans and the air. It would have caused a mass extinction on a scale almost unimaginable. The vast global empire of anaerobic microbes that had ruled the Earth for over 1 billion years was systematically wiped out, pushed to the margins of existence, into deep-sea hydrothermal vents, deep underground in rocks and aquifers, or in the oxygen-free guts of animals that wouldn't exist for another 2 billion years. It was the first, and perhaps most profound, mass extinction Earth ever witnessed. The perpetrator was life itself. But as with so many of our cosmic catastrophes, this ending was also a dramatic new beginning. The oxygen crisis forced innovation. Some microbes evolved defenses, enzymes like superoxide dismutase that could neutralize the toxic forms of oxygen. Others went a step further. They learned to not just tolerate oxygen but to use it. They evolved a new, incredibly efficient form of metabolism, aerobic respiration. This was the ultimate recycling. These new microbes would consume the organic carbon made by the cyanobacteria, and using the oxygen that was now everywhere, they would burn it for energy, releasing carbon dioxide and water. This process yielded almost 20 times more energy than anaerobic fermentation. It was like the difference between a smoldering ember and a blazing bonfire. This new, high-powered energy source would eventually become the foundation for all complex life, including us. Every cell in our bodies today uses this same ancient oxygen-based power system. The consequences of the GOE didn't stop there. The rise of oxygen had a second shocking side effect. It may have triggered a global ice age so severe that it nearly killed the planet itself, an event called Snowball Earth. How? By destroying the methane. Remember those methanogens, the ancient microbes that produced methane? Methane is a fantastically powerful greenhouse gas. For billions of years, it had been keeping the faint young sun's Earth warm. But oxygen reacts with methane, breaking it down into carbon dioxide and water. Carbon dioxide is also a greenhouse gas, but molecule for molecule, it's much less effective than methane. So, as oxygen levels rose, the methane blanket was torn away. The Earth's thermostat crashed. The planet plunged into a deep freeze, with ice sheets possibly reaching all the way to the equator. This is the Huronian glaciation, which lasted for a staggering 300 million years. The very life that had caused the oxidation now nearly perished in the freeze it induced. It's a stark lesson in the interconnectedness of our planetary system. Finally, high in the atmosphere, the oxygen did one more thing. It was bombarded by the sun's ultraviolet light, which split the O2 molecules and allowed them to reform into a new molecule made of 3 oxygen atoms, ozone, O3. Slowly, a thin, fragile layer of ozone began to accumulate in the stratosphere. This layer acted as a powerful sunscreen, blocking the lethal UV radiation that had previously made the land surface uninhabitable. For the first time, life had a chance to leave the protective waters of the oceans and begin its conquest of the continents. So, the Great Oxidation Event was a catastrophe of the highest order. It was a genocide for the ancient world of anaerobes. It was a planetary pollution event that triggered a global ice age. But it was also the pivotal moment that made our world possible. It provided the high-energy fuel for complex life, it created the protective ozone layer, and it set the chemical stage for every animal, every plant, every fungus, and every one of us to eventually evolve. We are the children of that catastrophe, breathing the poison that became our lifeblood, living on a planet forever transformed by the stubborn, sun-harnessing power of a tiny revolutionary microbe. Staying on Earth but moving forward in time, we come to catastrophe number 8, the Permian-Triassic extinction event, also known colloquially as the Great Dying. To truly understand the scale of the Great Dying, we first have to picture the world as it was just before the catastrophe. It was the end of the Permian period about 252 million years ago. The continents, driven by the slow, powerful churn of plate tectonics, were all crammed together into one gigantic supercontinent called Pangaea. This meant that much of the land was far from the life-giving sea, creating vast, harsh, and dry deserts in the interior where only the hardiest creatures could survive. Yet, life had flourished, finding its way into every possible niche. The oceans were teeming with a spectacular array of life. Elaborate corals built great reefs. Shelled creatures called ammonites with their spiral shells drifted through the water, and trilobites, those ancient armored arthropods, scuttled along the seafloor. On land, the rulers were not dinosaurs. They were yet to come, but strange and magnificent proto-mammals known as synapsids. Some were hulking, barrel-chested herbivores like the tusked Dicynodon, while others were fearsome predators like the sail-backed Dimetrodon. It was a stable, complex, and thriving world, a world that had no idea it was living on borrowed time. The trigger for the apocalypse was not an asteroid, though one may have played a role, but something far more prolonged and terrifyingly violent from within the Earth itself. In a region that is now Siberia, the planet's crust literally began to tear itself apart. This wasn't the eruption of a single dramatic volcano like Mount St. Helens. This was something almost impossible to comprehend, a series of volcanic fissures, a catastrophic rupturing of the Earth's skin that erupted continuously not for days or years, but for nearly 1,000,000 years. This event is known as the Siberian Traps. The scale of the lava flows is beyond human imagination. Scientists estimate that enough lava poured out to cover the entire continental United States in a layer of rock over a kilometer deep. Just sit with that image for a moment. But the lava itself, destructive as it was, wasn't the main killer. It was what the lava carried with it, and what it set fire to, that would doom the world. As the molten rock ripped through the Earth's crust, it passed through and cooked vast layers of limestone, which released staggering amounts of carbon dioxide, and through coal beds and oil deposits, which it effectively set on fire, pumping even more greenhouse gases and ash into the atmosphere. Think of it as the planet accidentally lighting its own fossil fuel reserves on fire, a process that took a natural cycle and turned it into a runaway train. The amount of carbon dioxide released into the ocean atmosphere system was almost unimaginable, with estimates suggesting levels rocketed from around 400 parts per million to a suffocating 2,500 parts per million. For context, before the Industrial Revolution, our atmosphere had about 280 parts per million of CO2. Today, we are at about 422 ppm and are deeply concerned about the consequences. The Permian world was hurtling toward a level 600% higher than our pre-industrial baseline. This massive influx of greenhouse gases initiated a runaway greenhouse effect. The Earth's thermostat was broken and the planet began to heat up relentlessly. Global average temperatures soared, with scientists estimating an increase of around 6 to 10 degrees Celsius. That's 11 to 18 degrees Fahrenheit. The poles, which were already ice-free, became warm, and the tropics became lethally hot, with average equatorial surface temperatures potentially reaching a scalding 34 degrees Celsius, 93 degrees Fahrenheit, or more. This warming had a cascade of deadly consequences. On land, the climate went haywire. Weather patterns shifted violently, turning lush, rainy regions into arid wastelands and vice versa. The intense heat also damaged the protective ozone layer high in the atmosphere, allowing harmful ultraviolet radiation from the sun to pour through to the surface, damaging the DNA of plants and animals and causing mutations in plant spores. Acid rain, formed from the volcanic sulfur dioxide, began to fall, scorching plants and poisoning lakes and rivers. But the true heart of the tragedy was in the oceans. Water, as it warms, loses its ability to hold dissolved oxygen. As the superocean Panthalassa heated up, it began to suffocate. The oceans lost about 80% of their oxygen, and about half of the seafloor, particularly at deeper depths, became completely oxygen-free, or anoxic. This created vast, toxic dead zones where nothing that needed to breathe could survive. At the same time, the enormous amounts of CO2 being absorbed by the seawater made the oceans more acidic, a process we see beginning today as ocean acidification. This acidic water attacked the shells and skeletons of countless marine organisms, literally dissolving the very foundations of their existence. The base of the marine food web, which depended on photosynthetic plankton, collapsed. Without sunlight, nutrients, and with acidic, oxygen-poor waters, These tiny organisms died off in unimaginable numbers, pulling the rug out from under the entire oceanic ecosystem. The kill mechanism, therefore, was a multi-pronged assault. It wasn't just one thing. It was everything, all at once. For marine life, the primary cause of death was likely suffocation. As their metabolism sped up in the warmer waters, they needed more oxygen, but the water itself held less. It was a cruel, inescapable trap. Creatures that lived in colder, oxygen-rich waters near the poles were almost completely wiped out, as those conditions simply vanished from the planet. On land, the story was equally grim. The soaring heat, the acid rain, the UV radiation, and the collapse of plant life, starting with the great tropical forests which were completely wiped out and replaced by tiny weedy plants, meant that herbivores starved, and the carnivores that preyed on them soon followed. It's no wonder that an estimated 96% of marine species and 70% of terrestrial vertebrate species were driven to extinction. Entire branches of the tree of life were pruned away forever. The mighty trilobites, who had survived for hundreds of millions of years, vanished. The bizarre and wonderful proto-mammals that had ruled Pangaea were decimated, with most lineages disappearing entirely. The recovery from such a profound catastrophe was not swift. The planet was locked in a hothouse state for millions of years. The destruction of the world's forests, especially the tropical carbon sinks, was a key reason this heat persisted for so long. With the plants that normally helped absorb CO2 gone, the planet's thermostat was stuck on high. The first signs of life in the early Triassic were not of vibrant ecosystems, but of disaster taxa. These were tough, generalist, weedy species that could survive in the harsh, post-apocalyptic world. In the oceans, a few hardy clams and snails persisted. On land, the most famous survivor was a humble, dog-sized proto-mammal called Lystrosaurus. It wasn't particularly specialized or impressive, but its generalist nature and ability to burrow perhaps allowed it to survive the worst. For a time, Lystrosaurus made up an astonishing 90% of all land vertebrates, a stark monument to a world laid low. True ecological recovery, the return of complex ecosystems with diverse predators and prey, and specialized creatures filling specific niches, was agonizingly slow. It took at least 5 to 10 million years for life to begin to rebuild its former complexity, and some estimates suggest it took up to 10 million years for the carbon cycle to truly stabilize. This slow recovery is a testament to how thoroughly the planet's life support systems had been damaged. But this blank slate, this emptied world, was also an opportunity, and into this void stepped the reptiles, particularly a group known as the archosaurs, the ruling reptiles. They possessed key evolutionary advantages that allowed them to thrive in this new, challenging world. Many had evolved an upright posture with legs directly under their bodies, which made them more agile and efficient runners than the sprawling proto-mammals. More importantly, evidence suggests they had a more efficient respiratory system, similar to that of modern birds, which allowed them to extract oxygen more effectively from the thin, compromised air. They were simply better equipped to breathe in a suffocating world. So from the ashes of the greatest catastrophe life has ever known, a new world order emerged. The age of the proto-mammals was over. The age of the reptiles had begun. These archosaurs would diversify into a spectacular array of forms: crocodilian relatives, flying pterosaurs, and eventually, walking among them, the first small, inconspicuous dinosaurs. The Great Dying, in its terrible wisdom, had cleared the stage for the next great act in the history of life. It is a stark and sobering reminder of the fragility of our global ecosystem, showing how interconnected the atmosphere, the oceans, and the land truly are. And as we look at our own world today, with its rising temperatures and changing oceans, the ghost of the Permian whispers an urgent warning from the deep past, reminding us that we hold the power to protect the delicate balance that makes our world a living one, or to break it. And speaking of dinosaurs, our 9th catastrophe is the one that is most famous here on Earth: the Cretaceous-Paleogene extinction event, the day the dinosaurs died. About 66 million years ago, a chapter in Earth's history came to a sudden, violent, and definitive close. The culprit was an asteroid, roughly 6 miles wide, traveling at a speed of around 40,000 miles per hour. It struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The energy released upon impact was equivalent to billions of atomic bombs detonating at once. The immediate effects were local but apocalyptic. A fireball that incinerated everything within hundreds of miles, and mega tsunamis that scoured coastlines across the globe. But the real catastrophe was what happened next. The impact vaporized a massive amount of rock, launching it high above the atmosphere. As this superheated ejecta rained back down across the entire planet, it heated the upper atmosphere to oven-like temperatures, triggering a global firestorm that likely burned a significant portion of the world's forests. Then came the long, dark winter. The immense quantities of dust and soot thrown into the atmosphere blocked out the sunlight for months, possibly years. Photosynthesis ground to a halt, collapsing the food chains both on land and in the sea. The planet cooled dramatically. Acid rain fell. The non-avian dinosaurs, along with pterosaurs, large marine reptiles, and countless other species, perished. This catastrophe, while an ending of an era, was also a new beginning. It cleared the way for small, adaptable mammals to emerge from the shadows and eventually diversify into the world we know today, a world that includes us. It is a humbling thought that our own existence is a direct consequence of this random, catastrophic intervention from space. So, we arrive at our final catastrophe, the one that lies in wait, not in the distant, abstract past, but in the definite future. It's a story whose first page has already been written and whose ending is known. This isn't a tale of a random asteroid strike or a sudden galactic explosion. It is the carefully scheduled natural conclusion to the life of a star, and with it, the world we call home. Our sun, that faithful golden disk in our sky, the bringer of light and life, has an expiration date, and its death will be a slow, majestic, and utterly devastating event for our solar system. To understand this, we need to think of the sun not as a static, eternal ball of fire, but as a dynamic, living engine in a constant state of battle. For the past 4.6 billion years, and for the next 5 billion or so to come, the sun is in its main sequence phase, the stable adult period of its life. Imagine a perfectly balanced scale. On one side, you have the immense force of gravity, which is constantly trying to crush the sun inward, pulling all of its vast mass toward its core. On the other side, you have the tremendous outward pressure generated by nuclear fusion in its heart. Deep within the core, where the temperature is 15 million degrees Celsius and the pressure is crushing, atoms of hydrogen are being slammed together to form helium. This process releases a staggering amount of energy, which radiates outward, pushing back against gravity's relentless pull. This balance, this stalemate between gravity and fusion, is what makes our sun stable. It's what has allowed life on Earth to arise and flourish for billions of years. It's a cosmic miracle of equilibrium. But this can't last forever. The sun's core is like a fuel tank, and it is steadily burning through its hydrogen. In about 5 billion years, the hydrogen in the core will begin to run critically low. The central fusion factory will start to sputter. This is the moment the balance is broken. With less fusion energy pushing outward, gravity gains the upper hand. The core, no longer supported, will begin to contract and collapse inward under its own weight. Now, here's a fascinating and counterintuitive bit of physics. As the core contracts, it doesn't cool down. It actually heats up dramatically, like a bicycle pump getting hot when you compress the air inside it. This new, intense heat from the collapsing core does two things. First, it raises the temperature of the shell of hydrogen that still surrounds the core to the point where that shell suddenly ignites in a furious new wave of hydrogen fusion. This shell burns far more fiercely and uncontrollably than the core ever did. The second thing this heat does is it causes the outer layers of the sun to receive a massive, explosive influx of energy. They will respond by expanding, and I mean expanding on a scale that is almost impossible to visualize. The sun will begin to swell into a red giant. It will not be a gentle growth. Over the course of several 100 million years, our sun will inflate to a diameter at least 100 times its current size, and perhaps as much as 200 times. Its surface will cool, turning from a brilliant yellow-white to an ominous glowing red. But don't let the cooler color fool you. Its total luminosity, its overall energy output, will increase thousands of times. As it expands, the inner solar system will be consumed. Mercury, the closest planet, will be the first to go, vaporized in an instant, swallowed whole by the advancing stellar atmosphere. Venus will be next, its thick clouds and rocky surface dissolving into the sun's outer layers. Then, the turn of our Earth. The science is still being refined, and there's a subtle gravitational dance that might occur. As the sun loses mass in its outer winds, its gravitational grip on the planets will weaken slightly, potentially allowing Earth's orbit to drift outward a little. It will be a race against time. Will the Earth move away fast enough to avoid the advancing edge of the red giant sun? The most current models suggest it's a race we will lose, but only just. Even if our planet isn't completely engulfed, it will be skimming the searing hot outer fringes of the solar atmosphere. The result is the same. The sky on Earth, if anyone were left to see it, would be a terrifying blood-red dome. The sun would fill the entire heavens, from horizon to horizon. The heat bathing the planet would be far greater than the inside of a pottery kiln. The oceans would not just boil, they would be stripped away entirely as superheated steam, lost to space. The rocks themselves would melt, the continents turning into a global lake of lava. The atmosphere would be ripped away by the ferocious solar winds. Every trace of our world's geology and biology would be utterly erased. The planet would be sterilized, melted, and reduced to a scorched cinder, a dead rock orbiting inside the outer atmosphere of its dying star. But the sun's death throes are not over. The helium-rich core, now compressed and heated to an incredible 100 million degrees, will face its own destiny. It will become hot and dense enough to start fusing helium itself, slamming helium atoms together to form carbon and oxygen. This is a much more frantic and unstable process. For a time, the sun might find a new shaky balance, but it's short-lived. The helium fusion will proceed in violent pulses, causing the sun to shudder and eject more of its mass into space. It will become a variable star, pulsating in brightness, its outer layers becoming bloated and loosely held. Finally, in a last gentle act of violence, the sun will shrug off its entire outer envelope. These vast, beautiful clouds of gas, glowing with the intense ultraviolet light from the hot core left behind, will expand out into space for light years in all directions. This is the creation of a planetary nebula, one of the most beautiful objects in the universe. For tens of thousands of years, this cosmic butterfly will glow, a brilliant, multicolored funeral shroud for our star, visible from distant galaxies. And what remains at the center? The sun's core, now exposed. All nuclear fusion has stopped forever. It is no longer a star, but a stellar corpse, a white dwarf. This object will contain about half the original mass of the sun, but crushed into a sphere only about the size of Earth. A single sugar cube-sized piece of this material would weigh as much as an elephant here on Earth. It is incredibly dense and incredibly hot, initially glowing with a searing white heat from the leftover energy of its former life. But with no new energy being produced, it has only one path: to cool down. Slowly, over trillions upon trillions of years, this white dwarf will radiate its remaining heat away into the cold of space, fading from white to yellow to red, and finally to a cold, black, invisible cinder, a dark diamond in the void. The solar system, what's left of it, will be dark and frozen. The giant planets like Jupiter and Saturn, stripped of their atmospheres and scorched, may continue to orbit this dark relic in perpetual night. This is the ultimate catastrophe, not a random accident, but a guaranteed and natural part of a star's life cycle. It is the ultimate reminder of the transience of all things. Every mountain, every ocean, every living creature, every memory and monument of humanity is temporary on a cosmic scale. Our solar system was born in the chaotic collapse of a solar nebula. It nurtured life through countless other catastrophes, and it will meet its end in the gentle, yet utterly destructive embrace of its dying star. But in that death, there is also a strange beauty and a profound legacy. The carbon and oxygen forged in the sun's final fires will be scattered into the galaxy by the planetary nebula, destined to become part of new stars, new planets, and perhaps one day, new life somewhere else in the cosmos. Our sun's story, and our story with it, is just one small, beautiful verse in the eternal unfolding poem of the universe. So, there you have them, 10 catastrophes of cosmic proportions, from the birth of the universe to the death of our sun, from the violence that forged the elements of life to the impacts that shaped its evolution. It's a story of unimaginable power and destruction, but as we've seen in the cosmos, catastrophe is not just an end. It is very often a beginning. The Big Bang gave us a universe. The death of the first stars gave us the elements for planets and life. The impact that gave us the moon made our world stable. The extinction of the dinosaurs gave mammals their chance. The universe builds through destruction. It creates through chaos. It writes its most beautiful poetry with the language of catastrophe. So, the next time you look up at the silent, peaceful night sky, remember the incredible violence that crafted every single point of light and the fragile, beautiful chain of cosmic disasters that led ultimately to you being here to look up and wonder. Good night. Have a deep, calm sleep.